people joining online and watching the recording. Welcome to this awesome presentation about intelligent digital twins. And we are talking what kind of questions we are asking from experts and we want to be asking from artificial intelligence assistants. So to answer these questions, obviously the intelligent assistant needs to have access to data, and there's some difficulty we have, and the main difficulties with data is so on the side is one group is availability, accuracy, and confidence in the data we have, and this kind of group is addressed with something that is the digital twin paradigm, which I'm going to talk about a bit later. Then another difficulty is just transforming data to actual knowledge, to knowledge insights. So topics here are like, what is the context of our data? What is the data semantics, or like the meaning of data? And how do we collect expert knowledge in general and transfer it? And the last group I outlined is like data and knowledge management. So topics like findable, accessible, interoperable, and reusable principles, and just in general, the creation of knowledge silos and organizations. So as I said, like the first group of those challenges is addressed by a digital twin model. Yesterday we said that, one of the difficulties, like, what is the definition of a digital twin? And my subtenant is, oh no, not this again, not again to talk about what is digital twin, but kind of have to go through it. This is the definition I like originally from Michael Greaves, who actually introduced the digital twin conceptual model. And what Greaves outlines is basically digital twin is a model that consists of a physical twin, a digital twin, and it is based on two fundamental principles: duality, so there's this physical and a digital stuff, and a strong similarity. There's a communication channel between the physical entity and the digital entity. A more simple definition from IEA position paper: digital twin, or the digital counter, is virtual representation of connected physical asset. Very easy. But at the same time, what do we mean when we say virtual representation? So this is from Fei Tao. She introduces the concept of five-dimensional digital twin. So she outlines that the digital representation, or virtual representation, consists of data, services, models, and then a connection channels between all of these elements, and connection to the physical system. So one of the topics is addressing data, getting availability from a physical system through this connection channel. And then what we're going to talk about today is models and services. So unfortunately, like as we discussed also yesterday, very often, at least in academia or in publications, people focus on just models, like how do we model a wind turbine, but forget the rest. This is a classification we already mentioned yesterday of digital twins according to IEA, but based on the functionality of digital twins. So not digital twins are kind of created equal. And because the initial definition is so broad, people say it can mean anything. So it's useful to say, well, we can have different functional levels of digital twin. So on the basis we have just supervisor, we're just one connection, and we just collect data. Operational, where we collect data in like zero, what is the operational state of our physical asset. Next level, we include some simulation or prediction tools, where we can predict what will happen with our asset or simulate some of the missing data. And what I want to be focusing on this level, intelligent learning. So how do we incorporate some artificial intelligence? The ultimate level would be where we want to reach is autonomous management. So this is the topic where we talk about AI agents, but we are not there yet. So as promised, a little bit on connectionist versus symbolic AI. So on the left, it's a picture from a logical calculus of ideas eminent to nervous activity. It's a 1943 article by McAuliffe and Walter Pitts. And this is the beginning of modern, like what we know right now as neural networks. And this idea was later picked up by Rosenblatt in his idea of a perceptron. But unfortunately, due to several reasons, one of them probably mistakenly attributed to the book Perceptrons by Minsky, which said that, well, these kind of structures cannot represent all logical operations, and we tried to think called AI winter, where the idea of development of connectionist approaches was put on hold, and the development was not as much. And people focused while developing AI from this approach to a different approach, which is based on formal logic. Because we will see a lot of graphs today, but not all the graphs mean the same thing. So these are very different from another thing that comes from formal logic domain and area. This one, when we see like these kind of graphs, they are based on the predicate logic. So we have like subject, predicate, object. An example is, I don't know, host ID 001 subject is predicate, turbine object. And the way the reasoning occurs is by logic rules and by inference. So here I like list some proposition A, host is a wind turbine, proposition W has a model, and then we can do like a lot of inference, like A and B leads to B, A and B leads to B, not A leads to I, and not W leads to N, and so on, and we can draw some conclusions. What I want to stress is very different. This AI is very different from current large language models, and we'll see that why. And first, I will expand on the symbolic AI, on the one that is based on logic, because that's historically what was happening in the 80s until very recently, where we went back to the connectionist approaches. So the ultimate end for this logic-based approaches is something that is creation of ontologies, ontology graphs. So definition of ontology is like a formal, explicit specification of a shared conceptualization. When we say formal, we mean it's based on logic, it's machine understandable, interpretable. Explicit means everything is defined through propositions. And shared means it's a share between the different stakeholders, because obviously each proposition, whether it's true or not, is evaluated based on the shared understanding. Here's a small example of what you would call currently a knowledge graph, which is like an instantiated ontology. So we can see how it's built on this predicate statements. Wind turbine is a product has model, product model is another concept. And then we can say statements like, oh, this specific wind turbine, the one that was probably to ATH, is a wind turbine, and it has model that is event. And this another one is also a wind turbine, and it has a model. How this kind of expert system works is that by stating all of this, we can define some rules, and then we can infer that based on our model, and then the domain of has model relationships comes from product to product model, we can infer that this event ID7 object label is a product model. And that's what people are trying to do. It has a lot of pros. The pros are that this knowledge is explicit. It contains domain-specific knowledge. It evolves as new knowledge is added, and it's formally rigorous. So it's decisive, accurate, and interpretable. All kinds of inferences that we do on this symbolic AI have these pros. The negative side is it doesn't really scale well. When we build these very large networks of statements, and then we try to run formal algorithms, they become very slow. due to just the nature of those algorithms. Another big con is that it relies on expert human input. So every time we need to create this kind of knowledge or systems, there has to be an expert that has to be defining all of those things. And therefore, the knowledge is incomplete and some unseen facts will not be represented. And so because of those negative sides, and they were quite like roadblocks, and the increase in computation capability, people went back to the idea of the perceptrons, the one that started in 43. So people might not be aware, but modern transformers, modern LLMs, they are based on, it's an architecture that consists of these tokenizers, embedded layers, and then transformer layers, which have both the attention and they have a feed-forward network. And the feed-forward network is essentially the perceptron. It's a neural network. So what I want to make clear that these circles and arrows are very different from the ones in an ontology. It's essentially very different things. Here, in each circle, there is a number, and there's just like some mathematical operation, like multiplication, and just where in the previous one, each circle is a concept, and the relations are semantic relationships. So very different things at the bottom up. The positive sides, it's a very generalizable architecture. The original paper, all you need is attention, was for computer vision, was not for processing language. You can use transformer architecture for many other applications where it lends itself to well. The learning of these networks is algorithmic. You don't need human input. As long as you can define a function to which it learns, it will do it by itself, and it scales well. The inference is almost instantaneous, just multiplication of matrices. And we are pretty good at multiplying matrices with modern CPUs. The negative side is it's inherently stochastic model, so non-deterministic, famous hallucinations, black box models. We have no idea what those numbers mean. There is some work on interpretability of AI but it's quite difficult. And what most important for us right now, it lacks domain-specific knowledge. So when you put them side by side, it's quite clear that if you would have some kind of a hybrid system, there would the pros and cons would address quite well, right? If you take the symbolic one, that doesn't scale well, but the connection scales well. This relies on human input, this does it by itself, but the opposite is true. Here, we have all of these hallucinations and non-deterministic things, but the symbolic one provides the formal rigor. So it will be great to kind of combine them. And these are three main directions right now. I will not go into detail. One, because we don't have time, and two, because it evolves so quickly that probably in 2 months it's going to be irrelevant. But I can recommend this paper that kind of outlines the main taxonomy or main ways people are trying to do it. Three main directions are knowledge graph enhanced large language models, large language models augmented by knowledge graphs, and then some synergized approaches, which is people are not even sure how that will look like. This is the most like the holy grail, but people are not sure how it will look like. Knowledge graph enhanced LLMs include knowledge graphs in the training process. For most of the applications, it's quite difficult because the industry doesn't really have the capability to train large language models right now. Or when knowledge graphs are used on the inference stage on LLM, so like it's an intrusive thing. It requires a deep integration with large language model itself. So most of the work right now happens in this box of large language models augmented by knowledge graphs. And here we get into approaches where we just provide our knowledge graph as context, things like retrieval augmented generation, for question answering, for text generation, and so on. And Georgette will cover quite a few of these things in his presentation. So, as I promised, shifting gears, it's amazing that we can combine these two approaches. We need knowledge graphs for that, but there is one essential problem. We don't have knowledge graphs containing wind energy domain knowledge. We did a research, we looked into digital twins. We looked at our digital twins are classified based on the classification I showed before. So one thing, most of them are, as I said, focused on simulation. People just think about simulation. There were only one paper that was describing autonomous management digital twins and intelligent learning digital twins. One of those papers was going by Georgette. And what is even more important, all of these digital twins and decision support systems, they don't use semantic artifacts. When I say semantic artifacts, I mean ontologies or knowledge graphs. So they don't use explicit knowledge. So that is why we decided to develop a wind energy domain ontology as an alignment layer. I talked about it yesterday, briefly for people watching the recording. The wind energy domain ontology has to, we aim for it to comprehensively cover the wind energy domain, provide a middle alignment layer between top-level ontologies like basic formal ontology, AF4, information modeling framework, and the lower level ontologies for application-specific things. For example, failure modes, effects, and criticality analysis. And we want it to become the basis for failure data and to make the data AI ready, make it available for these hybrid systems. Very briefly, what I mean by this is that if we take the basic formal ontology, which is supposed to describe everything that exists, so BFO entities, anything that existed, exists or will exist in the future. The main two branches are like continuant and occurrent. Continuant and basically means something that exists continuously, and then occurrent some like events, some processes that happen. So if we just go by those two branches, we'll get whole areas of knowledge that we have to explicitly define. For example, object, and like things like wind turbine part, measurement station, measurement device, wind farm, balance of plant, supply grid. So all of these things defined. Here, I just define them as subclass, but there also can be a relationship between them, and then all of them can have subclasses, instances. So the idea is that wind energy ontology defines the top level concepts, and then there should be another lower level ontology, for example, wind farm system ontology that doesn't exist yet, but we hope it will, that defines these things in more detail to achieve higher granularity. Another thing that we might be interested in is sensor ontology, aligned with semantic sensor network, or like site one. Why is this important? I mean, just for example, yesterday we were talking about task 4.2, and one of the concepts defined in the taxonomy for the gearbox was the gearbox location of a failure, like where on the gearbox did the failure occur. And we would think that if I want to say, well, this failure occurred at some point, I would have a reference model where I can say, oh, generally people call this, I don't know, as a sun gear. But we run quickly into problems that, for example, in the Reliable project where they analyzed the reliability wind turbines, they defined 5 levels, hierarchical levels of components, and an ontology for mecha defined 4, and which one of them is being like just gears or some like aggregate. And then when we try to run some attribution or we try to do like analysis of data, we're not we have this mismatch. So we need to have a shared model that community accepts, or we need to have mapping between these things so that we can use the results of analysis from one source and port it to another and port it between applications. That's the last one in terms of continuance. Another one that unfortunately we want to develop is the wind energy stakeholder ontology. That one, and when we go to the other branch for the processes, is we are trying to do some work on developing activities and processes, so define them. And the last one, and not least, is the one which would be very useful. It would be definition of all the things that belong to something that is called information content entity. This would be the last one to develop because it relies on formalizing other concepts first. So because it contains things like model software. So if we are trying to say, or classify a software and do some mapping, or to do mapping of standards, as we discussed yesterday, we want to say, like, for example, if the standard applies to some component of a wind turbine, if the standard applies specifically to gearboxes or something like that, those things have to be defined first. So we expect it to be the last kind of thing that will get developed. So finally, very quickly, to the fun part, we took the ontologies that already exist and the knowledge that has been developed by some people, put it into as a context for large language models, and try to ask the assistant some of the questions and see how well it will do. With that context, one of the ontologies that we added called VASGraph, it had its own top level ontology, but it was developed for modeling offshore wind farms mainly. Another thing that I added was the blade damage ontology, and I imported some of the definitions by the work from EPRI group, the one that Noah mentioned. So like all the terms in terms of like what is a blade anomaly. I imported the taxonomy of wind turbine parts, and this model is quite simple. It just has the blade anomaly. It can belong to some category, and then that specific category or that specific anomaly can require some action, and it can have some effect, can have some cause, and can happen in some part of a blade. And some other the taxonomy of life cycle stages based on a standard. All of them can be found on Technoportal. So these are kind of the questions we try to ask. And I will not go too much into detail, but there are very specific domain industry questions. For example, according to the INSPEC 9103, what are the main life cycle phases of a wind power plant, and what are corresponding subphases? We had a question on blade damage. What are the categories of wind turbine blade damage according to EPRI? And what are actions required for category 4 blade damage? So if you would take just the vanilla ChatGPT 4.0 and not provide it any context, obviously it was not trained on these specific things. There is no way it can have this information. So for all of these questions, it happily hallucinated whatever it thought it was the answer to. When we added web search, it didn't manage to answer any of those questions either, with the only exception of the one with EPRI. That's the only reason, because it just gets such a nice web hits that the model just went to it just was getting a lot of context from the web pages it was getting from web hits. But if the web search of the model could not find it, there is no reason. Like it could get things like what constitutes substructure and foundation balance of station cost, there's no way that it would manage out of all the noise, out of all of the data and all the publications that exist on the internet to get a structured response. When we used the reasoning model, O3, so all models are reasoning models, they have internal chain of thought. The downside is that it takes quite some time for them, and it's computationally intensive. So we used O3 with web search, and it managed to answer all of the questions. It was actually hitting the techno portal where we stored all of the ontologies, downloading ontologies, processing them, and providing the answer. The downside is quite heavy. So it had to think, compute for like 2 minutes and 28 seconds to just answer a very simple question based on some specific standard. But when we provide all of this information as context in form of a knowledge graph, and our architecture talks to the knowledge graph right away without having this weird intermediate level of going through the web. And obviously, like if it is some company, they don't even want their information to be on the web. So it was much faster. The O3 because it already didn't have to sift through all the web results. And then we could even use GPT-04 mini because the emergent reasoning capabilities of even the smaller model, so for mini is much smaller model, it reasons, has internal chain spot for much smaller time. It was still was able to answer all the questions, but in a fraction of time. So like 15 seconds, 28 seconds to answer the same question. It would get into the ontology and the knowledge graph, write a query, process it, get the query result, and present it back in the formal language. So these are results, final thoughts. Are we there yet in terms of answering the types of questions I mentioned in the beginning? Not really, but we are getting there. The important outtakes is that structured data and knowledge is still absolutely necessary for futurized systems. They cannot, the models by themselves cannot solve it. And to do this, it will need an interaction between diverse domain experts. So data managers, data engineers, knowledge engineers, and data scientists. So thank you. And I will be happy to take questions.
Thank you very much. I hope it was interesting for everybody. I think it's really great work that Yuri's doing. Do we have any questions in the chat? No. So does anyone have any questions?
I've got a question. I've got a question. You didn't mention narrow language models compared with large language models. My understanding is large language models are very good for general kind of questions where it's consumed the internet, but when you want to work on a very narrow technical domain, as you're working here, you have to think in terms of narrow language models. Can you just comment on that and how that input into what you're doing?
Yeah, sure. It is possible to train an expert language model on your specific data as long as you have capability to do so, which computationally, I mean, to train even a narrow language model, I assume it's going to be quite costly. Not every company would be able to do so. And I just don't see that as much of a viable strategy. And to add to that, it's still like it still would be affected by these problems. It's still going to be inherently stochastic, non-deterministic, and it still would be a black box. We would not know what is happening in the background. So I really don't see this as a viable strategy, to be honest. I think that the advantages of this hybridization provides are just outweigh. Okay. Christian?
Sorry, I was on mute. In terms of you saying therefore that we really need to use the symbolic AI as a way forward in large language models to make that work and get the information, and effectively for a wind industry language model, somebody would have to create one to feed it to do the training, and then individual organizations could load all their data to be able to answer your type questions, as you said at the beginning, in terms of what's my expected lifetime of turbine A117. Is that what you're thinking in terms of the way this is going to go?
Yeah, I'm not sure I fully understood your question, but yeah, I just think that we do need to create some of the structured knowledge in terms of ontologies for future hype, and then the future systems will be hybrid. They will not be pure LLMs.
Yeah, I guess I'm just thinking if I'm an operator and I'm thinking I want to use, we all know that every CEO wants to use AI to help them improve their performance, and I'm thinking to answer your questions as a wind farm operator, where does that take us? And I think you're saying, you are going to need to load this kind of knowledge into your language model. You've just said that could be hard for an individual company to do. So if I'm a commercial operator, and we know there's lots of different models out there, I'm going to have to load that knowledge in. Then each operator can load their data, and hopefully that will then give them the answers they're looking for if they want to use AI to help them with their answer the question that you articulated at the beginning of the presentation. Yeah.
Yes, exactly. And in some cases, it's impossible to load that knowledge. Like the evolving data, like the data that comes from sensors, you're not going to be retraining your LLM every time you get some reading from a sensor. So the symbolic AI is good for this evolving knowledge. So some things like you just cannot put it into. So yes.
Okay, thanks.
I have a quick question, please.
Let's take one from the audience here, and then we'll go on. It's okay?
Okay, thank you.
Yeah.
Correct. A great presentation. I guess here within this slide, maybe you could comment a little bit about energy consumption between the two approaches, and maybe also you could also relate to the last slide where you have the tables, right? Where you were comparing the different approaches, and here you have time, but time is not always related to energy, especially if you compare the mini with the large one, right? Could you comment on the energy consumption enhancements based on the combination of the two approaches?
But I think time, I mean, it's not linear correlation, but it is quite correlated with energy. Like the longer the inference time is when the GPUs actually get spun up and are used. So the longer chain of thought reasoning time is actually using more energy.
Right. There's another dimension where GPT-4, right? Going to consume is a larger model, right?
Oh, the one
more than the mini.
without the reasonings. Oh, yeah. That one is a bit more difficult. Like I don't have it's very difficult to evaluate. And with cases like GPT-4, it's closed source and you're not running it yourself. To know that, we would have to run like something like Llama and to benchmark it to see actually also because the question, how much energy it's going to consume, it depends on how big the question and how much data it has to process. Like the size of a prompt.
The prompt.
Yeah, and the tokenization, it depends on tokenization. Yeah.
Oh, thanks.
I think Christian had his hand up as number one.
Yeah, thanks very much for an interesting presentation. I very much find this hybrid approach intriguing, potentially very promising topic. Could you go back to the slide with pros and cons? So one thing I was thinking about in relation to the symbolic approach is that in the early days, the AI community were trying to express the rules with first order logic, which is very expressive, but then it was not decidable. And then the ontology semantic web community converged on OWL because it's the decision logic is decidable, but then it's less expressive, and whether you could balance that gap with a hybrid approach, and also on the connectionist side, the computational cost, although it scales well, it's very computationally expensive. So like if there would be some ways to reduce the computational expense and also get around some of these problems where you run into situations where a problem expressed in a pure formal sense is not decidable.
Yeah, thank you for your question, Christian. So I feel like both of these topics are quite research areas in all themselves. I think the main thing I wanted to convey today is that I believe that these kind of hybrid approaches will be a way forward, and I'm not the only one. There are quite people in the industry who believe that. And I'm going to discuss it a bit even more in detail in the paper that is coming up. So you will see all the references, all the people who agree with me and people who don't agree with me.
I agree with you.
But in terms of, so let's do the connectionist first. In terms of computation, I know that there are a lot of research on that topic, and again, the field is so quickly evolving with things like the DeepSeek, where they introduce mixture of experts model, which does reduce the computation quite a lot. So there will be like a lot of strategies. I'm not an expert on these things precisely, so I'm not sure I can comment on them as much. It is true that the first order logic was the approach that semantic web is went was like, yeah, description logic because it is decidable. But I think ultimately there is no solution to the Turing problem. So I don't know if we will ever be able to fully address undecisiveness. So
Yes, fair enough.
Great presentation, and I'm glad we're on the slide because this is where I am too, is like algorithmic learning. That makes sense to me based on what we've done historically. And I'm excited about this too. I'm just thinking about like, O&M is predominantly driven by transient batch specific serial defects. So can you kind of frame how you would scale this up on symbolic side versus applying historical knowledge, algorithmic learning to define those metal inclusions and like, or is it just a matter of, is it because of where we are as an industry? And does this lend itself to a more mature industry? I guess these are the questions that I have when I think about making these types of transitions.
So if I understand correctly, your question, you're asking if wind energy industry can actually adopt or get into the symbolic part, because we are kind of like still very much on these.
I guess I'm curious what kind of rigor it takes. Like, are we talking about supply chain rigor or like sub-supplier level? And like, yeah, is it about getting access to that? And yeah, I'm curious how you would build this out to pick out like serial defects in a gearbox, for example.
Mm-hmm.
And that's a big question. So
yeah. It's difficult. So in terms of defining ontologies and defining logical rigor, that would have to be done by experts based on expert knowledge, and it has to be. That's exactly the task of this ontology development. So we are like at the tip of the iceberg, right? We're very closer to here, developing like, okay, what is the general things that happen in domain? What are the logical things that all the concepts we have to define? And then understanding like, I don't know, failures of a blade is a specific application, right? And those are limited. And then for each application, there would need to be some kind of formalization of knowledge. So for example, like I tried to do with the blade damage, right? It's not that difficult, I think, but it does require like certain mind shift for some people. It did happen much, as you said, it's the industry maturity also question. These kind of topics were much more driven in the biomedical community, like ontologies and knowledge graphs, and something like I've just adopted by biomedical community and the e-commerce domain. The good side is that all these technologies exist. People know how to do it. It's just a matter of applying it in the wind energy. So it is possible. We don't have to reinvent the wheel. George will show much more actually about knowledge graphs too.
On that note, we have to stop. We're 20 minutes over time. I know it's a really important topic and I didn't want to stop the conversation, but we don't want to shortchange the other people who were talking because we do have to stop at 1 o'clock, 12 o'clock, I mean. So any other questions for Yuriy, please ask in the break. We're having a panel discussion afterwards anyway, where we do have some time planned for Q&A. So it is 20 past. So my suggestion is a 20-minute break. So we start back at 22. We won't cut time on George's presentation, but we do have an hour for the panel discussion, so we just cut 10 minutes from that. I think that'll be okay. So yeah, see you all back in 20 minutes. Online people, see you soon.